Um, so welcome everyone. Yeah.
Okay. So good afternoon, everybody. Welcome to a new webinar from at my project. In this webinar, we have two parts. One presentation of two applications, both related to remote sensing and life. First, we'll have one presentation for Sarbi Sarma from Jülich, and then from Wojciech Stefaniak from Poznan. So it's my pleasure to introduce you Sarbi Sarma from Jülich ISEC. She is going to present the application on remote sensing, the use case we have on remote sensing. And as usual, please wait to the end of the presentation to make questions using the voice. If you want to send questions using the chat,
So Jesus, can I start?
Yeah, you can.
Okay. Thank you for giving me the floor. Welcome everyone. My name is Surbi Sharma, and I'm representing today the application from WP7 work package, remote sensing, in this webinar series. My affiliation is from Forschungszentrum Jülich. So today's agenda is I will go through each and every aspect of the application. First, I will introduce the application, then a little bit of overview and how we progress in the application. And then what are the computing characteristics? And then what are IO characteristics for our application, and a little bit of our notation on profiling and malleability. So let me start. And please feel free to interrupt me and ask any questions if at any point of time you feel that you do not understand anything. I'll be here to answer. And also after the presentation, I'll be taking up the questions as well. So starting with remote sensing, what actually is remote sensing? So the process of getting the data, not from the Earth, but from the satellites or the airborne sensors by sources of measuring the reflected and emitted radiations is usually the process of remote sensing. So we get the data. There are many satellites, for example, there are many European satellites. We all know that Sentinel-2 Copernicus program is there, and we get lots and lots of satellite data. So we have the opportunity to process the data and to get results, and we can do multiple learning techniques and classify and obtain maps that could be helpful and for applicative purposes. So here in our application, what we do is we acquire the data that is available from a satellite, and we pre-process the data. Usually pre-processing the data could be related to multiple things. There could be atmospheric corrections, there could be radiometric corrections, there could be upscaling, downscaling of the images, what we want and how we want, so that our algorithm understands the data. And then there comes the procedure of classifying the data, where we actually emphasize on having an algorithm. In our case, we are using a deep learning algorithm, could be machine learning, could be any sort of algorithm that could be used in classification. So here in this our application, we used EfficientNet, a deep learning algorithm, EfficientNet V0, and it's written in TensorFlow, and the application gives us the classification maps and also multi-label classification maps, and all the processing pipelines is parallelized using Horowot, and which makes use of nickel and MPI routines, and all of the classification was done on JSC's supercomputers. Could be for example, URLs and deep prototype model. So here, the data we used in our application is Big EarthNet data. It is obtained from Sentinel-2 image. It is a Sentinel-2 image product, and the data has that it was obtained from June 2017 and May 2018, and it's all over the Europe. And the data size is approximately 66 GB. The image patches consist of 125 tiles that is across all different countries in Europe. And each patch is annotated with multiple land cover classes that I have already mentioned, multi-labels. And here there were two, if you go to the website, there were two options. We just chose 19 labels for processing in this application. So the data, since we used a TensorFlow library, so the data was converted to TF records, and the TF records were, you can easily use the raw data, but we went for the TF records data and for this pipeline. These are the computing characteristics we go through in our application. So since our application uses a distributed framework and it is scalable, so we use Horovod for scaling purposes. And the library used, you can see, is TensorFlow on top of Keras. And since we use Horovod, so for workers communication, that means from for GPU or CPU communications, Horovod internally applies some of its own communication routines, and they are based on NCCL and MPI. And since Horovod does it on the top of Horovod, so we do not actually see all those things, and it makes the implementation on TensorFlow or PyTorch very easier. So here, just a little bit of detail on how it does. It uses NCCL for GPU to GPU communication, and MPI for CPU communication. And one worker is what I mentioned is one MPI process, and one worker is also equivalent to one GPU, which in our application. And the process nomenclature as the same as MPI, it's like rank and size, and for local GPU assignment, it uses local underscore rank. So here, I will go ahead with the distributed training that we used in our application, data parallelism. I will also explain this slide along with another slide here, hand in hand. So it might be that I would just transition between these two. So with distributed training, it was we implemented data parallelism. There are three kinds actually. There is one pipelining, data parallelism, and another one is model parallelism, but we stick with data parallelism. So here we divide the data into small chunks of pieces and input to each of this process. So what are these processes? These is something equivalent to one GPU. What we could say in data parallelism, there is a simple thing that we need to fit the model. The model has to fit in the memory of a single GPU. So here you can see, I will just explain the pointer. You could see this as one GPU. You could see as one GPU, you could see as one GPU or one worker, or you could say nodes as well sometimes. And the training process, how it goes through, it has a same model on each of the worker and a smaller chunk of data. The data is itself divided into multiple batches. And then it is processed and training. So let's see another slide and then we understand a little better how it happens. So I was explaining this one worker, this another worker, and another worker. So here we have different chunks or the batches or the mini batches of data that can go up to the number of workers. We divide the whole data into small portion of mini batches. So here, one mini batch is one worker will work only on its own portion of a mini batch size. That's what I mean. And here we could say at each worker here, at each worker, what will happen is that there will be a forward pass and a backward pass. In the forward pass, we implement some activation functions and local losses are computed. And also these weights and losses were optimized using stochastic gradients approach, and some gradients were calculated locally. And then they are synchronized. For example, once we calculate the gradients, they are synchronized using here this, you could say MPI, just like MPI all reduce, we had used here a ring all reduce mechanism. So here all the gradients are averaged, collected, averaged, and then were given to each of the models, so that their parameters get updated. And then we somehow, and then we calculate the optimized loss, and then we get an optimized results, sorry. So here with the procedure, we did scaling with Horowitz. This is the pipeline that we actually followed in our code. So first we initialize the Horowitz, then we pin each GPU to a single process. That is one MPI process. Then scale the learning rate by the number of workers. So let me explain you a little bit on the learning rate. So here we have multiple parameters on which the distributed training can depend on. But there are multiple challenges that we have to take care while performing the distributed training. Number one is that once we if we distribute the training, then the effective batch sizes, the effective mini batch size gets increased, because we have to increase the number of GPUs or the workers, and then we have to increase these effective mini batch sizes. So once we increase these mini batch sizes, the optimization by the stochastic gradient approach gets really trickier, and sometimes it can worsen the accuracies. So we have to tune the learning rate parameter or the learning rate schedule according to some warm-up scales, or sometimes we have to scale it with the number of workers, as we did here, and also then reducing it after some epochs. Maybe we did some warm-up phase, for example, from 1 to 3 epochs, and then reduces it afterwards. So this really helps to get a better results. So then we wrap the optimizer with the distributed optimizer function that Horowitz has to compute the gradients, and then we broadcast the initial variable states from rank 0, because we use rank 0 as the main role function, and then it distributes to all the other processes, and then we modify the code to save checkpoints. Usually we did it at every 10 epochs, and we did it only on worker 0, so that no other worker could corrupt them. So here, this is a code snippet that we could look into. So this is, we initialize the Horowitz training. So this is a Horowitz initializer, and then we get the GPUs or the visible devices. And then we created the model using Keras and efficient net V0. And we use the activation function as sigmoid because of the multi-labels. And then we found the rank in every summary. And also in that data processing, we used all the data processing pipelines that TensorFlow has to offer. For example, shuffle, pre-batching, etc. You could also see here. Pre-batching or mapping for any kind of transformation, initial transformations, and then calculate the batch size, batches, preparing the batches of the data sets. Jesus has a question. Do you have several GPUs per node or just one process GPU per node? That's a very good question. It depends. I would also cover it in the next few slides, but to answer you, for example, if we go in production, if you use Juvis, the supercomputer that is already in Jülich, it has 4 nodes, 4 GPUs per node. So if we say 1 node, so it would be 4 GPUs. And if we can also use just 1 node and 1 GPU, and that is also available in our test prototype that is on D. So it is upon us. So if I mention here 1 node, so that means 4 GPUs here. If does that answer your question, Jesus? Okay, yeah. And then we go for the learning rate adjustment, as I already informed you that if we are scaling it, so we would scale it with the number of GPUs. So here we perform the scaling, and then we wrap up with the distributed optimizer that OfferRoad has. We already using this Adam optimizer, and we would just wrap it. And then we compute the losses and create the models. Also, I would like to mention here that for the output files, we are using HDF5 files. And for the input, we are using TensorFlow TF records. So, and then we would start the training here and write the logs on worker 0 as already described in this pipeline. So now I would like to go through this. What our initial results of the application with the training on Juvis and Eureka. Both are the supercomputers here with this. And since one node I mentioned here is this contains 4 GPUs. So here 24 node means 96 GPUs. So the training time per epoch was calculated. And you can see that, of course, because the Juvis have higher capacity and higher nodes or in NVIDIA V100 16 GB. So and also the memory size is 196 GIV memory. And it is our production machine. So here on Juvis, the training time per epoch is already less. And we can see that as we increase the number of nodes, the application scales. But we could also see that after some point, it is not scaling linearly. So there is some non-linear patterns in scaling of the application here. And it is observed both on the Eureka and Juvis machine. And the time calculated is in seconds. So now I would like to go through what are the there is another question. Did you use Jugal Cluster Boost in Jugal Booster or Blue Reference? Yeah, that's a good question. We actually did it on Booster. I forgot to mention that. Sorry. Yeah, you that I think because I also got confused with Jewels and Jewels Booster. But mostly the similar results can be obtained. Jewel Booster is mostly used in production. Yes, you're right. Then the I/O characteristics, as I already mentioned before, the TensorFlow dataset API is used for input, and the output files are the HDF5 files. What I'm mentioning as HDF5 files are the checkpointing files that we already make at 1/10 epochs. So the file formats for input are TF records, and for this checkpointing file is HDF5, and the data read is around 66 GB or 60 GB. And because we also sometimes do the pre-processing and remove all the images that are with cloud and everything that we do not read. So around 60 GB would be the input, and written for the checkpointing is around 500 MB, and the data access pattern is sequential and distributed. I would like to make things very clear here. So the application was because we made the application some time back, so we tested in production. But for profiling, we were we did not have enough hours on the Jewels machine, and also at that time we were struggling that we should use test or the production environment. So first we did the profiling on directly on the test environment. So on the test environment, I would say we used Deep, which is also a modular prototype, and we use this extreme scale booster. The problem was that because it was sometimes under maintenance, and sometimes all the nodes are not available, and sometimes we are just left with a few GPUs to work with. We could not actually at that point scale on the GPUs to see how our the application would perform on scaling on GPUs. Rather, what we did for the initial results, we tried to make it on just one GPU. And then we obtained, we checked if we could change the number of CPUs per GPUs and see if there is a trend obtaining for the application, just for the initial results. Of course, it would change after we do the next step of the profiling. We would expect them to change. So these are just the initial profiling characteristic. We have already submitted the profiling characteristics, and we also discussed in our Wednesday's meeting. I think that was yesterday only. And we discussed that the profiling characteristics in details, what we obtained and how we obtained, for example, by changing this CPU per GPU to 1 or 2 or 3, etc., to 8, and then we try to obtain it. So we also try to look at the mean statistics table here, and we could see that there are some read operations, and also some because it was multi-threaded, so there are also threads working on it. And we could also see from the mean context events that a lot of read operation was going on, and definitely we could see a lot of read operations here. And this was, yes, on the yesterday's call, it was also verified by Jean-Baptiste that he has already compiled some of the profiling results, and he provided us with this image. I would like to cite this and also give him credits for this, Jean-Baptiste. And he also mentioned that it is quite similar that we have many read operations going on. That is, I think, also expected because we are reading at instance. Also, I would also like to point on one thing. Right now, we are also not using caching. We did not implement caching, at least for the profiling, but it is already there in our application. So right now, the profile results are without caching, and the profile result does not include GPU scaling as well. So I am assuming that in the later stages, when we actually scale it to GPU and also introduce caching, these results might look something different. Right now, I can only see that there are a lot of input, output, read operation, and then a little bit of GPU operation going on here. We could also try to look into it in detail with Jean-Baptiste and other Paratool members here. And last but not the least, I would also like to talk a little bit of how our code can or cannot, I'm not sure about it, but offer malleability. Right now, if you see that we have the application, and our application is built upon Horowod, and Horowod uses its internal library MPI and Nickel routines. So it's for the GPU and CPU communication. As I was also going through this tutorial from David's on the Flex MPI, and we could, and he talked about that we could use this Flex MPI and put all these commands with just the normal MPI code. But I'm not sure how our code could take all these parameters. Maybe we need some detailed discussion on that, since I'm not aware that how malleable our code is right now at this stage. I also try to look at these two links where we could actually try to change the initialized init pi and all these things, and we could try and look at these mechanism, so that if we want to integrate malleability with Horowod, we have to change some things in Horowod itself and implement that at the very early stage and not in the code itself. So that was my take on malleability. I would be really happy if there are any suggestions on this, and if we could work together to get into this more. So these are the references and acknowledgements I used in this presentation. And thank you. And I'm up for any questions.
Thank you, Sarvi, for the presentation. I don't know if you have any questions.
There is one question I could see here.
Yeah.
Would it be possible to start the application with different number of processes after checkpointing? Well, it is not possible at this moment, because we have to also we have to look that if we could tweak it, because right now what we are using is just writing the application, or for example writing the Slurm configuration, and we do not change it in between. So if for example, if the training gets stopped at some point, and if we have to restart the training, we could tweak it, but not in the middle of it, as I understand.
But then, Sarvi, if we would like to apply malleability to this application, it would be not possible once you have started, I understand, no? To make the learning.
Yeah. Yes, that was my concern itself. That's the reason I told you that I tried to look here, try to look here in that we have to go to, and we have to make changes in the distributed optimizer or Horowod itself, and it would be of no point. And we are not even sure how our application would react to it, at least at this point.
Okay. Okay. But if you are learning, I mean, if after some point you modify the number of processes, you could distribute the learning, no, the epochs or similar in. But you are making independent epochs in different places, or I don't know if I am asking for something that is wrong. Or I mean, I don't know the application very well, but.
Yeah, you can try asking it again. Maybe I could refer to you with this here. So one epoch is, let me make it clear to you. One epoch is that if we go to the whole forward pass and then backward pass. and the whole training is one epoch. So we have multiple, there can be multiple iterations. For example, if we have a training of 1,000 number of samples, so if our batch size is almost like 500, so there would be 2 iterations in one epoch. So one epoch is like just one time entire training, but it's not with optimized losses or something.
Okay. But you are executing several epochs or just one?
Yeah, no. We have trained it for the results I've showed you here. They were on 1,000 epochs.
1,000.
Yeah, no, so this is the training time per epoch. We measured it, but the whole application was on 1,000 epochs.
Okay, thank you. There is, I think, another question. Actually, it's not a question, it's a comment from David. Okay, so I don't know, you have more questions or no? Okay, so thank you, Surbi, for your presentation. You are the host. Please close the recording for the next presentation. Yeah. Thank you.
Question. I think you did not see that in the chat.
Yeah.
Okay. Yeah. Let me again go through this. There is a question. Horwood already supports elasticity. Where do you see the main advantages of using malleability in MPI for ring all reduced procedures instead of simply letting Horwood elastically reconfigure the resources at runtime? This is really interesting to study. First, for example, well, actually, this needs to be looked upon a little bit. I'm not sure if I would be answering it correctly, but I would rather try it. Right now, what our application is, we try to, for example, set these the configuration parameters, how much is available to us, and then it uses, because on ULs we pay for these machines and for all the nodes. So at one time, if for example per node, if you have chosen 2 nodes, so all the 8 GPUs available on that nodes would be like this. So we just try to enhance and push the training in every case. But yeah, this needs to be looked upon that if we could change this at the runtime, or if we would simply let Horwood change it at the runtime, how much it wants and how much effectively it could actually do it. So yeah, it would be interesting to see it in this respect as well. I'm not sure if I'm answering your question. You could ask me again if this is something related.
No, thanks. I think that clears it up. So yeah, just because we had used elasticity in Horwood before, and it works actually quite fine. But of course, if you're limited by Slurm in that case, then this is maybe another story. But it should be something you can keep in mind, because it works directly for the ring all reduce mechanisms and is using nickel down below, so that the GPU communication is automatically scaled up. And this could be something which could help you in deep learning workloads too, I believe.
Yeah. Thanks for this note. I would definitely like to look at it. Thank you. But we also
okay.
Try to look at how.
So there are more questions. Okay, so thank you for your presentation, Sarbi. It happens that I see the recording button, so I can control the recording. It doesn't was in my screen before, but now I can see it. So we will stop the recording of this presentation now, and we will start the recording for the next presentation in a second. Okay. Thank you, everybody. Thank you again, Servi.
Thank you.
No, you have to do it. I see the